One molecular formula, multiple compounds. What if I told you that the same molecular formula can give rise to different compounds with completely different properties? That's the magic of structural isomerism, where one formula leads to many possible structures. Hi, I am Dr. Swathi. Let's dive into structural isomerism like never before. Let me first explain you what is isomerism and why is it important. So the definition is isomerism is the phenomena where two or more compounds have the same molecular formula but different structures or arrangement of atoms. That means even though the molecular formula of the isomers is same, they have different arrangement of atoms. It is because the arrangement of atoms is different, they exhibit different physical and chemical properties. So that is the importance of the isomerism. So it is also critical for understanding chemical reactivity and also biological functions. Now this isomerism is broadly classified into two types. Structural isomerism, which is also known as constitutional isomerism, and the other one is stereoisomerism. So in case of structural isomerism, the compounds will be having same molecular formula, but they differ in the connectivity of atoms. That means one isomer, the carbon atoms may be present in straight chain form, while in case of other isomer, the carbon chain may be present in the form of a branched chain, that is branched molecule. So both might be having the same molecular formula, but the connectivity of atoms will be different. In case of stereoisomerism, compounds will be having same molecular formula and same connectivity also, but they have differences in the spatial arrangement of atoms. That means in case of stereoisomerism, even the connectivity is also same. So let us consider two isomers. One is this and the other compound is like this. Okay. So in the first example or isomer, let us say functional group hydroxyl group is present on the right hand side, while in another stereoisomer, the same functional group may be present on left hand side. Similarly, in one isomer, a group may be present above the plane, and in another stereoisomer, the same group, that is A, may be present below the plane. So that is how the isomers will be having same connectivity, but the spatial arrangement of atoms will be different in case of stereoisomerism. That means they mainly differ in three-dimensional arrangement of the atoms. Okay, so that is how structural isomerism will be mainly focusing on the two-dimensional structure, while the stereoisomerism is focusing on the three-dimensional structure. Now coming to the structural isomerism, again it is classified into 6 types. So they are chain isomerism, positional isomerism, ring chain isomerism, functional isomerism, metamerism, and tautomerism. So let me explain about these types one after the other. So the first one is chain isomerism. Here the isomers differ in the arrangement of carbon atoms or skeleton. That means one isomer will be present linearly, the carbon chain will be present linearly, while in another isomer it is a branched carbon chain. Let me explain this with the help of an example, that is butane versus isobutane. So both these are hydrocarbons, that means these two compounds are made up of carbons and hydrogens only, so they belong to the class of hydrocarbons. And also these two compounds are having same molecular formula. But yet, if you see the arrangement of carbon atoms, so in case of N-butane, the carbon atoms are arranged like a straight chain. While in case of isobutane, we are getting a branched chain. That means it is like the methyl group, last methyl group of N-butane. Okay, when it shifts onto the second carbon, we get isobutane, which is a branched chain molecule. Okay, so even though the molecular formula of the compounds is similar, the arrangement of carbon atoms is different. So that is the reason these isomers will be exhibiting different physical properties such as boiling points and melting points. The second type of isomerism is positional isomerism. So as the name itself indicates, the compounds are isomers, means having same molecular formula, but they differ in the position of the functional group on the carbon chain. So the example is 1-butanol versus 2-butanol. So as you can easily make out, both these compounds belongs to the class of alcohols. And the molecular formula is also similar, that is C4H9OH. So in case of 1-butanol structure, the hydroxyl group is present on the first carbon, while in case of the other isomer, the hydroxyl group is present at the second carbon atom. So that is how the position of functional group is different in case of positional isomers. So because of this change in the position of the functional group, the molecules or the isomers will be exhibiting different physical properties. So you can see here 1-butanol boiling point is 118 degrees, while in case of 2-butanol, the boiling point is 99 degrees. So because of this positional isomerism, compounds or the isomers will be exhibiting different physical properties. And coming to the chemical reactivity, because both these compounds belongs to the class of alcohols, they will undergo similar type of reactions. For example, they will undergo esterification, but their rate of reactivity will vary. So in case of 1-butanol, it belongs to the class of primary alcohol, whereas 2-butanol, it belongs to the class of secondary alcohol. So the rate of reactivity of this primary and secondary alcohols will be different towards esterification reaction. So their physical properties are different, and also the relative rate of the reactions, okay, will also different in case of positional isomers. The next type of isomerism is known as ring chain isomerism. So here the isomers differ between an open chain structure and a ring structure. That means one isomer will be present in open chain form, while the other isomer is present in cyclic ring form. So let us consider an example, that is propene versus cyclopropane. So both these compounds are having the same molecular formula, C3H6. But in case of propene, it belongs to the class of unsaturated hydrocarbons, alkenes, where the functional group is a double bond. In case of cyclopropane, it's a cycloalkane derivative. So all the three carbon atoms are connected in the form of cyclic ring form. Okay, and this cyclopropane can also be represented with the help of geometrical figure triangle. So here these two compounds are having the same molecular formula, but because the functionalities are different, they will be exhibiting different physical and chemical properties. For example, in case of propene, because it belongs to the class of alkenes, it will undergo electrophilic addition reactions, while in case of cyclopropane, it will be undergoing free radical substitution reactions. So that is how ring chain isomers will be exhibiting different physical and chemical properties. The next type of isomerism is functional isomerism. So isomers will be having same molecular formula, but they will be having different functional group. That is why this particular isomerism is known as functional isomerism. The example is ethanol versus dimethyl ether. So the functional group itself will be different between the isomers. So the first one is ethanol, where an ethyl group is present, which is attached to an alcoholic functionality. So that is ethanol structure. Well, in case of ethers, the functionality is oxygen. On either side, it is attached to methyl group. So this is dimethyl ether. So in these two compounds, if you see, first compound is having hydroxyl functional group. So it belongs to the class of alcohols. While the second compound is having O functionalities. Okay, so that means it belongs to the class of ether. Okay, because the functionalities are different, they will be exhibiting different chemical behavior. So in case of metamerism, isomers differ due to the different alkyl groups attached to the same functional group. That means compounds are having same molecular formula and same functional group. Okay, but yet they exhibit different properties. It is because the arrangement of alkyl groups across the functional group is different. For example, diethyl ether versus methyl propyl ether. So both these compounds molecular formula is same, that is C4H10O. In case of diethyl ether, two ethyl groups will be present on either side of oxygen. Okay, so as you are aware, ethers general formula can be written as RO, R or R prime. Okay, so here both the alkyl groups are present on either side of the oxygen functionality. So it is known as diethyl ether. Okay, now if you shift one of this methyl or methylene group to the other side, then the 2 carbon chain becomes 3 carbon chain. Okay, so here this side 3 carbons are there, and here because of shifting only 1 carbon is present. Whereas in case of diethyl ether, So one side of the oxygen, 2 carbons are present, the other side 2 carbons are present. So the overall molecular formula of these two compounds is similar, but the arrangement of alkyl groups across the oxygen functionalities are different. Okay, so that is the reason the boiling point of diethyl ether is 34.6 degrees, while the boiling point of methyl propyl ether is 38.8 degrees. So they exhibit different physical properties such as boiling points. Now the last type of structural isomerism is tautomerism. So in this, the isomers will be existing in dynamic equilibrium due to the migration of atoms within the molecule. So as a result of migration of atoms within the molecule, okay, here functional group shift occurs. So as a result of functional group shift, one isomer will be present in keto structure while the other isomer will be giving an enol form. So that is why tautomerism is also known as keto-enol tautomerism. Let me give an example for this. Acetaldehyde versus vinyl alcohol. So you can see the structure of acetaldehyde. So that is CH3CHO. This is the structure of acetaldehyde where the functional group is a keto functional group. Okay, so this is the keto form of the tautomerism. Okay, so this is keto form. While the other molecule, if you see, it is vinyl alcohol. This can also be written like CH2 double bond CHOH. Okay, so the CH2CH is known as vinyl group, which is attached to OH functionality. So it is known as vinyl alcohol. So if you see the functionalities, a functional group in this particular vinyl alcohol, so it consists of an alcohol functional group which is attached to an ene portion. Okay, so it is ene plus ol, it is known as enol. Okay, so vinyl alcohol, the functional group present is enol, while in case of acetaldehyde, the functional group is keto. Okay, so how this functional group shift is happening? If you see, out of the 3 hydrogens of methyl group, 1 hydrogen is migrated onto the oxygen. So double bond O, it becomes OH. And wherever C single bond is there in the acetaldehyde structure, now that becomes a double bond, carbon-carbon double bond. That means in the acetaldehyde structure, wherever single bond is there, that will become double bond in case of vinyl alcohol and vice versa. So that is how this bond shifting occurs, and as a result of which a keto form will be converted to enol form. Okay, and these two forms are always in dynamic equilibrium with each other. Okay, so this keto-enol tautomerism plays an important role in the biological systems and also in organic reactions. In summary, isomerism leads to compounds with identical molecular formulae but different physical and chemical properties. The key types of structural isomerism include chain, positional, ring chain, functional isomerism, metamerism, and tautomerism. So understanding these variations is very, very important for predicting the behavior of the organic molecules. Thank you so much for watching this video. If you feel that this video is useful to you, like and share it. Subscribe my channel so that you will get notifications whenever I share my next video. Till then, take care and I'll meet you in my next video. Thank you.